In this video, we're going to take a look at the iStore instruction. And so I've copied here, this is the table containing our instruction set for our ISA from page 4-16 in the notes in Canvas. And so the instruction we're interested in this video is this iStore. And so one thing that we'll notice that's different than the iAdd instruction that we considered previously is that our iAdd instruction didn't have any operand, right? So everything our iAdd instruction was doing was related to the stack. So it popped two things from the stack, added them, and then pushed that back to the stack. Our iStore, on the other hand, has some operand, this var num, which we can see is 1 byte in length. And so that's because we're now popping a word from the stack and then we're storing it back into a local variable. So we have to know where that local variable is. And so let's take a minute to talk about what this instruction looks like as it's coming into our MBR register. So to do that, we can talk about our ISA instruction stream. And so our ISA instruction stream is a byte stream. And so ultimately then these are going to be the bytes that go into our MBR register. And so recall ultimately the operation here is we have our ISA level program in some memory called the method area. Each byte represents an instruction. Our PC is pointing to the location in the method area. It's retrieving a byte, which is an instruction, and putting it into our MBR register. Our MBR register is then using that to set our MPC, our microprogram controller, which then selects the correct micro instruction from our control store, which then controls our data path for one cycle. So coming back to this ISA instruction stream though, here we're going to have 2 bytes, right? Because we have 1 byte telling us that we're doing an iStore instruction. We have 1 byte, which is going to be our var num. So let me draw a rectangle and then just sort of bisect it. So the first byte is going to be indicating that we're doing this iStore operation. And so what that is we're going to have some number hex 36. So let me write here in this first box, we want to do iStore. So what that looks like in the computer is that's just going to be hex 36. The second byte of the instruction, the operand, is just going to be our index. And so this is actually going to be indexed from our LV pointer. So index from LV, and the reason for that is our LV, recall, is pointing to the bottom of our stack, or it's our local variable frame. So if we index from there, we can get to the appropriate local variable. So for example, if we used our index 2, we'd be going to our third local variable, assuming we started counting at 0, right? So 0, 1, 2, we're at our second, or our index of 2, our third local variable. Now, of course, there are more instructions that came before this that I'm not showing, right? So we have bytes that came before that, and we'll have bytes that come after this. For something we're going to talk about a little bit later on, it is going to be helpful to have some variable that is sort of a stand-in for the number of our PC. So let's say this iStore instruction was located at address in our method area. And so then our index would be at address n plus 1, and whatever came immediately after that would be at address n plus 2, n plus 3, so on and so forth. And then on the other side, on the left, we could say before we got that iStore instruction, we had some instruction that was located at address n minus 1, something that was located at n minus 2, so on and so forth. So these are just our addresses in the control store. Sorry, not in the control store, in the method area. So addresses in our method area, which contains our ISA level program. And so this is what our PC points to. What PC points to. So essentially our PC contains then these addresses, which of course will actually be some number, but here I've just left it in to be general. So now we can look at our actual sequence of micro instructions, which is going to be executed with our microarchitecture. And so we notice here we have 6 micro instructions. And so what that means is we're going to have 6 cycles through our data path to execute this iStore instruction. So we have 6 micro instructions, or 6 cycles. So we have iStore 1 to iStore 6. And so what we're going to do is we're kind of going to track our progress. So over here on the left, I've got sort of a simple example stack. On the right, I've got some relevant registers from our microarchitecture. which are part of our data path, of course, and we're going to sort of see what happens as we're stepping through this. One thing that's going to help us a little bit too is I'm going to write in our main, so our main micro instruction. And the reason for that is, of course, we talked about every sort of micro instruction sequence is going to end by going back to main. And so in main 1, it's just one single micro instruction. We have PC being incremented. So PC equals PC plus 1. So we're going to the next ISA level byte. We're also going to initiate a fetch. And we're going to go to MBR. And so recall, as we talked about on page 4-6, any type of memory reference is going to take at least 2 cycles, right? We can't use what we're asking to fetch until 2 cycles later. So of course, when we're saying go to MBR here, we're not actually going to the MBR that we fetched here, but rather we're going to the MBR that was already loaded. And then we're just initiating a fetch because we know we're going to need that next byte eventually. So let's come down here and fill in some of these registers, which we already know the values of. So of course we can see in our example stack, we've got our SP over here, which is pointing to the top of the stack. So we can put that address of that top of the stack in our SP register. So that's going to be hex 118. So hex 118. Similarly for our LV, which is pointing at the base of the stack, our local variable frame, that's pointing to address hex 104. So I can put hex 104 in my LV. The TOS register is just containing the value which is currently at the top of the stack. So in our TOS register, we can just put -200. So of course we talked about that's helpful because sometimes that prevents us from having to make a memory read. We don't necessarily know what's in our holding register. We don't know what's in our MAR or our MDR, so we'll leave those blank for now. Our PC register is actually going to have some value which is going to be n plus 1. And the reason for n plus 1 is, remember, we were pointing at n. And so n was what we're using here. We've brought that hex 36 into MBR. We're going to that instruction. But we've also incremented our PC here. So now we're pointing not at n, but now we're pointing at n plus 1. So we're pointing at that index value. So our PC has a value of n plus 1. Our MBR, at least as we're starting, and so let me maybe write this down here. So this is at the start of Istore 1 is what we're representing right now. So at the start of Istore 1, we've not had enough time to finish this fetch. So we still have the old MBR value, which is going to be that hex 36. And so that hex 36, of course, is just this value, which indicates the Istore instruction. So there are our registers at the start of Istore 1. So now let's start working through these 6 micro instructions and see what's happening. So of course, remember what we expect to be happening is we're popping a word from the top of the stack and we're storing it in some local variable. So we can't use that MBR value yet. We can't use that index, right? So we've initiated a fetch to get this index value into MBR, but we can't use that yet because it takes 2 cycles, right? And so really this is a little bit incorrect. So it's saying that MBR contains the index. Really this isn't available to use until the next cycle. So not available until our Istore 2 line. So currently, like I have drawn here, our MBR is still hex 36. But what we're doing is we have H equals LV. So we're assigning our LV into our holding register because we can look ahead, we see we're adding, we know that H always has to be one of the 2 things if we're adding, with the exception of incrementing or decrementing by 1. So what we can do is we can go ahead and put our LV value, which is going to be that hex 104, into our holding register. And so really that's all we've done here. So I'm going to go ahead and erase this. We'll say now instead of at the start of Istore 1, we're looking at the start of Istore 2. So of course that H register gets loaded at the end of the cycle where Istore 1 is. And so we talked about that again with our timing diagrams. I believe that was back on page 4-4 in the notes on Canvas. And so now let's look at our Istore 2 line. So now what we're doing, and so I should mention too, at the very end of Istore 1, we've also loaded in that MBR register, so it's ready to use in our next case, in our next instruction. And so I don't have a specific value, and I'll mention why I'm not doing that in a minute, but instead I'm just going to put this as index. And again, coming back up here to our instruction stream, all we've done is we've loaded whatever this value is. And that's going to be, again, some number such as 2. And that's just going to be variable 2, local variable 2 in our stack, where we want to store this variable we're popping from the stack. So we've got now, at the start of Istore 2, we've got index and MBR. So what we're doing now is we are saying, let's take MBRU, which is the unsigned version of MBR. So we're putting the unsigned version onto our B bus. We're adding that with H, and we're storing the result in MAR. And so again, I'm going to be kind of vague and keep this index, and I'll mention why that is here in a second. But let's go ahead and just update our MAR, and that's going to be hex 104 plus our index. And again, the index is just some number indicating what variable we have there. So that's what it looks like after we've executed that Istore 2. So now let's move on and let's say what is going on in our Istore 3. And so of course, what we hope is that this MAR register is containing the address where we want to write to. And so let me go ahead and mention where that comes from. So if we look at, and let me just verify real quick this is the right spot. So if we look at page 4-5, so page 4-5 in the notes on Canvas, we talked about sort of the special way that MAR register addresses words. So remember, our MAR is addressing words instead of bytes. So for example, if we were to add 2 to that LV axis, we're not actually just going up 2 bytes, but rather we're going up 2 words. So instead of just going up 2 bytes, now we're pointing from 0, 1, and maybe we're pointing, our MAR is pointing to this position here if we had the index of 2. So we're pointing to hex 10C. So let's just say, for example, that's the case. So that's where our MAR is sort of pointing to at the moment. So let me maybe just add that in here, even though typically we don't show the MAR as being a pointer with it pointing to the stack like that. Okay, so we're at that point. So our MAR has been set to point there. And of course, what we're setting up to do is we're setting up to write a value to that location, because that would be, for example, local variable 2. And so sure enough, in Istore 3, what we're doing is we're saying MDR is equal to, so MDR is equal to top of stack, and then we're going to initiate a write. So the first thing that we're doing is we are putting the top of the stack, and so again, we're pulling this from the register, not from the actual stack itself, but we're pulling that from the register, and we're putting that into our MDR register, so negative 200 in this case. And so now what's going to happen is, remember, our MAR MDR register combo is used to write or read memory data words. So we're pointing at some address, we've got our data loaded into MDR, so we're setting up to sort of write into that spot. And sure enough, we initiate that write in that Istore 3 cycle as well. But remember, it takes a couple cycles, so this won't actually be written there until a couple cycles later. And again, that goes back to the timing that we saw on page 4-6. Okay, so now that we've got that initiated, you might think that we're sort of done with what we had to do, right? Because if we come back up here to the description of the instruction with our Istore return, what we're doing is we're popping a word from the stack and we're storing it in a local variable. So we pop the word from the stack, we stored it in a local variable, but we actually have a couple other things that we need to do, or there are a few things. So we need to update our SP, right? Because we popped this from the stack. So we now should have a new top of stack. So this should move down 1. We also need to update our top of stack register because our SP is pointing to a different location. And then another thing that is very different from our iadd instruction is we're also going to have to increment our program counter, because currently that program counter is still pointing at the index. But of course, we want our code to be able to eventually execute the next instruction. So we have to move our PC, increment our PC to point to the next instruction. So let's step through our last 3 micro instructions that make up Istore and see how we do all of those things. So looking at our Istore 4, and so let me come down here and let's adjust this to say this is our Istore 4. So what we're doing is we are saying sum operation SP minus 1, so we're decrementing SP minus 1. We are now setting that value into SP and into MAR. And so of course the reason we're doing that for SP should be obvious, right? We just talked about we want to move our stack pointer down by 1. The reason we're doing it into MAR is because eventually we'll have to read in a new value to our TOS register, and we want our MAR to be pointing to that position. And then sure enough, here at the end, we're initiating a read. And so remember again, that read is going to take 2 cycles before that value is in the register. So we've not actually changed anything. At the end of iStore 4 is when those registers get loaded. So we could say really that's the same thing as at the start of iStore 5. So at the start of iStore 5, we see the effects of that SP minus 1. So our SP minus 1, and again, that's going to be going down by a word. So really this is going to become hex 114. And so what I can do is I can move this down by 1. So now the top of our stack pointer is pointing here. We have also adjusted our MAR to point to that point as well. So now that is going to be hex 114. So we can just move, we can get rid of this, and let me move this up here. So we can just say our MAR, maybe let me put it right beside there. So our MAR and our SP are both pointed to that same location, and we initiated a read. So that's what our registers look like. We still have to wait for that read to happen, right? So nothing's happened yet, but we're getting there. So now let's move on to our iStore 5 instruction. So let me clear that out. So now in iStore 5, we see we're incrementing our PC. And again, we talked about the importance of that as we need to move on to the next instruction in our ISA level program. We're also storing that back into PC, of course, and then we are initiating a fetch. And so what that is of course we need to get that instruction, whatever we're pointing to. So we've set our PC to point here. Now we need to get whatever that instruction might be, and we're going to move that into our MBR register. So again, that PC register is going to get updated at the end of the cycle. So we can come over here and we can say, now let's look at the start of iStore 6, end of iStore 5. For our purposes right here, what we're considering it's sort of the same thing. So we can update our PC register. So our PC is now going to be n plus 2. So we're pointing to the instruction past the index value. We also notice that our write has finished. So at this point, we have finished that write. And so what that does is now where our write, so our MAR, and let's see, gotten a little bit ahead of myself here. So my MAR in the previous line, well, we were already set up to write to the address where the MAR was, so it was using that old MAR. So it's a little bit confusing because I've moved this MAR here, but we were already set up to write to that specific address where our MAR was pointing before, which we had down here. So now that write completes, so that value is going to be -200. So we've stored that into a local memory, local variable. And so that's what we look like at the start of our iStore 6. So then the final instruction there, our iStore 6, is only going to be updating our TOS register. So now let me get rid of our highlighting here. So now what we're doing is we have our TOS register, and we're just setting that equal to MDR. And so our MDR, now at the start of this as well, our read has finished. So our MDR is going to contain, in this example, 46. So whatever our MAR is pointing to there. And so at the end of iStore 6, at the start of the next instruction, that's going to be stored in our TOS register, 46. And again, the idea is that's going to maybe save us a memory reference down the line. And the other thing too is we don't see it quite here in iStore 6, but at the very start of our next instruction, so that'd be during our main 1 instruction, our MBR is going to be adjusted to whatever that instruction was, again, that was following our index. All right, so that's sort of the basic operation. And then of course we go back to main 1, and then from main 1, we're gonna be jumping to whatever the next instruction was, and that's just kind of how the process flow happens. So one thing that I want to mention is we can come back and we can take a closer look at this index byte. And so note, of course, that it is 1 byte, right? So we have our index is just 1 byte. And so of course that limits us in terms of how many local variables we can address. So we can only store into the first 256 local variables. And let me say first 256 local variables. And so of course that's just a factor of, we have 8 bits, right? So 2 to the power of 8 gives us 256. That wasn't an issue in this sort of really simple example stack I had here, but of course some functions might have some larger stack where that could become a problem. It turns out we do have a way to get around this. If we need to address local variables that are further away, then we have this wide variation, so we can use this prefix instruction, and we can combine that with our Istore to look at local variables, or store into local variables that are further away from our LV pointer. And so that's what we'll look at in the next video. And so I'll mention as well that our iload and our iload combined with our wide instruction are very similar to the Istore. We're just doing a sort of the opposite operation. Instead of taking from the top of the stack and putting it in a local variable, now we're taking a local variable and putting it onto the stack.